All right. Hi, everyone. Welcome today. So today we are excited to have Ian with us to lead a session on the creation, evolution, and formalization of new notational systems. And Ian is an assistant professor of human computer interaction at the University of Montreal, affiliated with both Department of Computer Science and Operations Research at MILA. He also founded the Montreal HCI group and developed ChainForge, a popular visual programming environment for prompt engineering and LLM evaluation. And Ian's recent work focuses on LLM evaluation, human AI grounding, and pen-based notational interfaces. And he was, before joining Montreal, he was a postdoc at Harvard with Professor Elena Glassman. And in today's talk, Ian will walk us through a set of fundamental questions regarding notational systems, such as, how are new notational systems created? How do they evolve? And what does it mean for notation to become formal? And perhaps importantly, how might a better understanding of these processes inform the way we design interfaces? With that, please join me in welcoming Ian, and I'll take it away.
Sure. Thanks for that introduction, Sang-Ho. So I don't think I'm going to get to answers for all of those things. As I was creating this talk, I sort of realized that, as I'm doing a paper on this, I sort of realized that these are really large questions, and there's a lot one could write about. So I'm just going to preface by saying that. Let me share my screen. Wonder if I can share. Okay. Let's see if I can just share my desktop. Can you see this? Can you see if it changes a slide?
Yes, it does.
Okay. Okay, good. Sometimes it doesn't. All right. So these are some early thoughts, as it says here. And I'll get into sort of the motivations for why I'm conducting this work. And I'll probably just we only have enough time to get into some of the patterns that I'm starting to see from doing this work on the evolution of notations. So I'd like to start by giving you a concrete example from my own life of how notations have appeared in design work. So I've been sort of kicking around the idea of creating this game to the left. It's probably never going to become an official game. But I've been kicking around creating this idea of a farming sim, which is set on Mars. And there's a number of interesting, to me, facets of this kind of game, where, unlike if you're familiar with Stardew Valley, I wanted to sort of take the farming sim genre and have it where you're managing an ecology of things that can naturally evolve. So plants can spread, animals can reproduce, and you're really more of the manager of this ecology rather than the more static management that you find in more contemporary farming sims. And while I was thinking about the design of this game, I was reading this book by Michael Sellers, Advanced Game Design. What Michael Sellers does in this book is adapt system dynamics theory to game design, particularly resource management in games. So how does this work? He gives an example of this kind of diagram, which showcases the relationship between predators and prey in ecological systems. So here we have lynx. The lynx eat the hares reproduce, and then the hares, the presence of the hares, which are eaten by the lynx, increase the lynx population. Right? And he adapts this to game design. So you have these reinforcing loops like in Monopoly, where the more money you have, the more properties you can own, and therefore you get more and more money. Or in RPGs, people might be familiar with, you gain a level, then you need to get a number of XP in order to get to the next level, and then you lose all your XP and you increase one level. So I was sitting one day and I was thinking, this farming sim is becoming very complicated. It's becoming difficult to see what the dynamics are. And I wanted to sort of see how applying this framework could help me think through the problem of creating this game design. And so here's a sketch that I created. It's exactly as I created it. I didn't like sort of touch it up for this talk, where I was trying to adapt that notation that I had sort of learned from Sellers to this new situation. And in the process, I didn't just adapt the notation verbatim, I actually made extensions to the notation. So I think the key thing here is this extension of the notion of a constraint. So in the original notation, you could have that, the more seeds you have, the more seeds you can plant in the ground, but whether you can plant seeds in the ground here is mediated by the fertility of the soil, right? So I started to realize that there's situations in which I wanted to extend this notation. This isn't something that I saw in the book. Similarly, I started to create these informal modifications where now there's dashed lines, and I think dashed lines mean like money or something. And so when you have a dashed line, you can like sell rocks, I guess, and you can sell them for money, and then the money is a resource that you can use to produce, to buy seeds. So from this practical example, which I hope gives you a kind of sense of the problem space that I'm talking about, right? This isn't just something that occurs in this one example, but I think it's something that occurs every day as we work together through practical problems. We adapt notations that we have seen, we create notations in an ad hoc basis, and my question for the HCI community is, how can we develop systems which support this natural creation of new notations, of extensions of notations? Can we develop systems which are more interactive and dynamic, which help me evolve or formalize my notation over time to iron out ambiguities, maybe help me share my notation? And so this is sort of the original insights that I had going into this project. Now, I'm going to take a big step back. The step back is that notations are everywhere, as we know. They appear in different forms, right? This is a picture to the right of a multiplication table, which appears in Sumer way back before Christ. And to the left, you see more modern notations, like sort of structural notation in chemistry and Feynman diagrams over here. Throughout human history, we've used notations in order to think, but also to communicate and coordinate action. In HCI and user experience research, I think the predominant ways in which that line of research has sort of dealt with notations has been through this cognitive dimensions of notations framework, which was introduced by Green, Blackwell, and others. People here are maybe familiar with this. This is more of a heuristics framework, a sort of heuristics evaluation of existing notations. But it's a post hoc diagnostic tool. It's not actually grounded in empirical evidence of notation development. And so while it's useful for us to analyze the affordances of existing notations, it doesn't give us a theory of how notations evolve. So for this work, I'm starting to ask these more fundamental questions of, how do notational systems that we're all familiar with, that I just showed you on that other page, how do they come to be? How do we come to see something like logic notation as a quote unquote formal notation, right? So what is the process of development of new notational systems? Why are notations created? What is that initial process like? So are there like common patterns? How do notations become formalized over time? What does that even mean? And what insights overall might this empirical knowledge have for us going forward? So interestingly, as I started to do this work, I realized that we really, in HCI and more broadly in computing, we throw around this term formal all the time, right? We're like, oh, this is really formal. We need to formalize this, right? Oh, this is an informal idea, right? And I really haven't seen a treatment of really what that means. I think there's implicit connotations that the formal is more precise in some way. I think we all can sort of agree. But is there a sort of social character to the use of formality? So usually in HCI, we sort of position formality as a spectrum or a scale, right? So an informal idea might be, give me Lisp code to process a metro ticket, you type into ChatGPT, and then to the right, you get the formal representation, which is an actual runnable program. And this is something we would consider formal, right? And there could be stages in between where you have a kind of pseudocode, for instance, different steps of the code before it's actually encoded into a formal notation. But this is the overall way we are looking at formality. And it's indeed what appears in the history of HCI at Chi 1994. You see this work by Shipman and McCall. They also, I think, wrote the paper on formalization considered harmful, where in this particular case, they show to the left here is the informal, right? And to the right, in their particular case, they were looking at like schemas, relational schemas. So for them, the formal representation was like a relational schema. Now, the difficulty with this is that it actually collapses a dimension. So I found it more useful to not think of, informal and formal as a spectrum, but rather to sort of question, well, how did we arrive at the formal thing to begin with, and to tease that out explicitly. So here to the right, we have a dimension of what we might call creation, the actual social construction of a new formal thing, which is a longer process than the typing into ChatGPT and getting an answer. And on the top, we have just a dimension of translation. Translation to an existing formal representation that we already agree exists and communities already use, right? Practically speaking, nowadays, unlike that mathematical tablet, nowadays we have notations are everywhere. They're all around us right now, right? So on our computer screens, there's all these different notations that are going on. There are graphical icons, there's natural language. And so practically speaking, there's never a pure vertical movement nowadays. It's usually this kind of series of translations and diagonal movements, right? And so what are these movements like, and are there patterns that we can observe in these quote unquote formalizing movements? So how is this vertical movement or diagonal movement achieved? So this was very theoretical, but I've felt that this square of formality helps me think through the problem and helps ground us on what we mean by formal a bit more. So what I've done now, so what I'm going into, and so this is active work, right? Please suggest, notations that I should look at. What I'm doing right now is a kind of comparative historical analysis of the evolution of different notations in different fields. So sheet music notation or dance music notation, Laba notation, from programming notations, Feynman diagrams, everything that I can sort of think of. Chemical notations are really interesting to explore because I think they're less reflected on. To some extent, finite automata, whatever is most well documented, I will say, as a secondary source. So what I'm going to do is just go into some findings today, and then some early thoughts that I think are most helpful for the group, and then we can have a sort of discussion and commentary on what I've presented. Are there any questions so far? No, okay. Okay, so, and again, this is sort of early stuff, and I'm simplifying it for the purpose of the presentation. It's a lot to throw at you right now, but I want to sort of provide you a little bit of framing. There does seem to be overall stages of notational development across notations throughout history, which kind of parallel the development of language. So you have an initial creation period followed by rapid iteration, rapid testing on different tasks and situations that's in the local area of the inventor. So there's usually either one inventor or usually some kind of small community which is incubating the notation. Then finally, it's like released in its initial version. And there's usually a practice of dispersion and branching. So when new communities sort of get the notation, because they're working together only in their local environment, especially before the advent of the internet, they would sort of branch off in their interpretation of the notation, and also the notation itself would evolve in a different direction. So you'd see this kind of branching emerge. Finally, in order to maybe control this branching, you'll start to see institutionalization happen. Standards committees will be set up for the notation if it becomes popular enough, right? It will spread to education, and the practice of encoding it in textbooks is also the practice of standardizing it. And finally, we'll see it emerge in software, right? So there will be reified, like Feynman diagrams or molecular notation are reified in specific software that allow you to enter them in. And so the notation sort of hardens over time. This is the broad level view. I will say that there's patterns at each of these stages. There's a lot to go into at each of these stages. I'm just mainly going to focus on the creation stage because I think it's most interesting for us right now. Okay, so I'll go into some early patterns and feedback. Important context before I get into the first pattern. Nazmis Saqib, who's a member of this group, I think a year ago or over a year ago now, suggested that I read this book when I told him about this idea. And I think this book is really enlightening. If people are not familiar with it, you should really read it, or read, at least the beginning parts of it to get the general idea. And so this book is by Lakoff and Nunez, traces the origin of mathematics into humans' embodied cognition. So how they understand the world in an embodied way. And they mobilize this notion of conceptual metaphor. They're actually adapting previous work on conceptual blending, which, to be honest, I find a little bit complicated. But they adapt this previous work, and they have this notion that metaphor, these sort of chains of metaphors, play a really key role in the invention and use of mathematical notations in particular, and mathematical concepts. So I just wanted to point out, you should see Saqib's work here. There's two kinds of metaphors that they point out, and I'm going to give tons of examples in a second. Grounding metaphors and linking metaphors. So what are these? So here's an example of a notation that Damien actually told me about, which was it's one of the most recent notations that I've seen, which was invented by colleagues, I think in France, to try to standardize gestures in the literature, how you show different gestures. And so it was presented at Chi 2023. They've done work since then. This is a good example of a grounding metaphor. So you see here to the right, it very clearly, these little like kind of Morse code-ish dots symbols here, this sort of dashes. It looks like Morse code almost. You can see how these 5 dashes, you see one is sort of below the others and how it maps to the hand. So there's like a visual perception here that the thumb is here, it's a little bit below the other digits, right? This kind of abstraction is what we would call a grounding metaphor. We're grounding it in this case, a embodied visual perception that is familiar to all humans, or all humans who are sighted, about this sort of about this sort of position of the fingers, right? So you can see this very clearly, and from here they of course create more extensions, right? So this is not something we're that familiar with here, but they start to extend from this base notation to try to describe movements of the hand. Another quite vivid example of a grounding metaphor appears in Koch and Kissinger's work on quantum category theory, quantum diagramming. And they have this notion of a yanking theorem. So they take string diagram theory, which was originally, I think string diagramming, originally kind of created by Roger Penrose to some degree, although it's difficult to determine. And you can see to the left here, they create the notation such that when we're looking at it, we see it as a string, right? And we see it, if we yank the string and it becomes taut, right? It becomes a line. They create the mapping to mathematics such that that actually works in mathematical thought. One new thing that they do, which is quite interesting, so they adapt the existing base notation. So in this notation, in the original notation, there are just boxes, not trapezoids. There's just boxes. And so if you imagine boxes being rotated through lines of a string, once it's rotated 180 degrees, it doesn't retain memory of its orientation, right? But what they want to do is they want to retain memory of that orientation to represent the transpose of a function. So as these sort of shapes go around the beads of a string, as they describe here, they have cut off the end. So now it stores the orientation, right? We can remember whether the function is a transpose or not as we move it along like beads on a string. And the similar yanking theorems apply here. So here's another example of how our embodied understanding of what would happen to this shape in this string that we develop kind of as kids then reemerges in a notation. Any questions at this point? Okay. There are also linking metaphors. Linking metaphors are what, most of their book traces. A linking metaphor is, at least the way I understand it, is you have an existing notation or an existing conceptual scheme that's known in science or mathematics. It's already an abstraction. And you are taking a different situation, so like chemistry, and you are now trying to just sort of map chemistry or map architecture onto this new situation or this old situation. So you're trying to map chemistry onto mathematics notation, for instance. And in fact, the origin of modern molecular formulas in chemistry comes from mobilizing this kind of linking metaphor. So this is actually the original page to the right, a picture of the original page where Berzelius introduces this notation for the first time. So we see here, we're familiar with H2O. In order to form a compound of H2O, you have 2 times hydrogen plus oxygen, right? And there's a history around this where at the time, for various reasons, chemists were trying to mathematize or make chemistry seem more mathematical, I think in part to get away from the perceptions that it's just alchemy, right? The sort of negative perceptions of it's just sort of magic, right? Another example of a linking metaphor is seen in dance notation. You can see it really vividly in this drawing by Noust above. Here, the development of Laba notation by Laban adapted quite clearly the sheet music notation that we're familiar with, right? You can also see this in Benesch movement notation, which actually retains this look of the staffs here, the staves. But what Laba notation does is actually changes this linking metaphor. It actually breaks the linking metaphor. And this is something we see in notational development. So let me go into this. So we have this initial linking metaphor, right? So we're creating a notation for the first time. So what do? We look at notations around us and we try to encode the situation in those notations, right? And then we realize that there are some problems with this. This notation is hard to read in some ways. For this case, what do the vertical dimension mean here? How does the vertical dimension map to dance moves, right? It's a little difficult to understand how that would be achieved. So in the early process of Laba notation is actually the flipping sideways of sheet music notation. Quite literally what they did is they took sheet music notation, they started developing it, and then this doesn't really work. It's difficult to understand. Why don't we flip it sideways? And in the process of flipping it sideways, they created a new sort of grounding in embodied cognition, a grounding to how we as humans understand the body going horizontally. right? So when we look at another human, we see, you know, hand, arm, shoulders, chest, shoulder, arm, etc., right? And we see that as a horizontal movement. And so similarly, Lab notation takes that understanding. The left side of the body is expressed here on the left, the right side is expressed on the right, which is only made possible when you partition space in this horizontal way rather than vertical way, right? So this new sort of embodied metaphor is only made, this mapping is only made possible through actually breaking a core component of the original notation. This is something that really surprised me. I still don't fully understand this. So the origin, it turns out, the origin of modern neural models in AI comes from the perceptron, which emerges from this particular paper by McCulloch and Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity. It's one of the most famous papers in all of computer science. And you can see in the way, this is the first time these sort of diagrams appear, although, you know, I'm being careful there. I'm not sure, they don't have references if they've seen this somewhere else. But you can see quite clearly a resemblance between this notation and neurons seen under the microscope. You see these axon terminals with the little dots here. You see these emerge again here. There's no reason why they need to use this notation to discuss what they're discussing in this paper. This is a paper on like formal logic, essentially. This notation is then adapted by Klein later on, reused in order to prove a theorem of equivalence between finite automata and regular expressions. So believe it or not, the origin of regular expressions comes from diagrams like this, which is really shocking to me. And so it emerges from a grounding metaphor in, believe it or not, you know, microscopic images of neurons, which are then reused and sort of adapted over these chains of adaptation to the point where we might not be able to even trace back what the original influence was. So you see these sort of metaphors appear in how people talk about these notations, right? So this is Roger Penrose introducing this sort of string diagramming notation. He talks about it as an arm and a leg, you know, transforming these functions into arms and legs, quote unquote. We can join these arms and legs. He makes a linking metaphor. Of course, it's adapting it to mathematics. He makes this metaphor, oh, now we can just put a plus, just like we can do in mathematics. We can just add the diagrams like this. Okay. Now, once you've established a notation, that notation, whether it's formalized or not, that notation can then become extended and reused elsewhere. One of the ways in which the notation is extended is to a new perceptual channel. So it adds a kind of dimension that wasn't used in the original notation. So here we have from Crum-Brown, this is the origin of structural formulas in modern chemistry. We have, we've seen before the molecular formula, and now all of a sudden there's a vertical dimension that's being introduced. This is literally like the next page to the right here. There's a vertical dimension that's introduced here to the equations, and then all of a sudden we start to see graphs, right? And from there, structural formulas were, there's more than just that, but structural formulas were introduced. Similarly, in programming, you know, we might see this case where informal practices that are used again and again become part of the formal notation. One example of this in programming is how Python takes whitespace and formalizes it. It becomes part of the actual semantics of the language, whereas in C, you didn't actually, you know, the whitespace didn't actually have any formal meaning. You might, of course, also extend or add a new variant to an existing perceptual channel. So when Feynman was first creating Feynman diagrams, there weren't like quarks and gluons. I'm not sure if they knew about them or not, but he didn't introduce this notation for gluons or the Higgs boson, right? Instead, those came later, and people extended his notation using the exact same perceptual channel of a line or a trajectory, but just creating a different texture on it. So now gluons are springs, Higgs bosons are dashes, this kind of thing. One thing you'll see in notation development, which is really interesting to see, is we know of Feynman diagrams. People here are probably familiar with them. But it turns out at the exact same moment that Feynman diagrams are being created, in Japan, they were creating transition diagrams. So for the exact same purposes as Feynman diagrams, there was an alternative in history of this different kind of diagramming practice. And so there's interesting insights that emerge from that. Finally, I will say, as a notation becomes formalized, it becomes, I guess you could say informally, it becomes more and more nitpicky about how you interpret the notation. The contestation of an evolution of notation becomes like almost hard to read because you need to be very firmly enmeshed in how the notation should be used and read in order to understand why there's a discrepancy to begin with. But you see both cases in which the notation sort of branches out because the person using it has a fundamentally different belief system than the person who created it, right? So different beliefs about the world and phenomena in the world, different philosophical beliefs about how the notation should be interpreted, which you see on the right here. So this exact same notation could be read in different ways by different schools of thought. Okay. So I sort of, went through the gamut. This is my final slide. I don't have anything else for now. So, my question to the community is this helpful to you? How can we think about applying this knowledge towards developing new interfaces, right? What more would you like to know about the evolution of notations? Is there things that I haven't mentioned here or comments on what I've mentioned so far? Yes. Oh,
Matt, go ahead.
Yeah, hi. Yeah, thanks for sharing all this. This is fun stuff, a topic of interest for me. You mentioned that obviously metaphors are a very important part, or like are an important part in notational systems because, well, if you're dealing with something abstract, you have to bind it to something, and we use metaphors. And part of what Lakoff's whole thing is that like how a lot of reasoning happens through metaphors, and they happen more often than we imagine. I think one thing that might be worth pointing out is that, especially for Lakoff, like spatial metaphors are uniquely effective and common. And so if you look at languages, like every language has spatial metaphors to talk about things like time and so on. And in the context of a notational system, like a spatial metaphor has the advantage of also being something that you can map to the page, right? Because if you're talking about a visual notational system, then it has that advantage. And so, Lakoff makes this claim at some point in one of his papers that like all of conceptual reasoning is, or abstract reasoning is a special case of using spatial metaphors, which is an ambitious claim, but holds up better than you might expect.
Thanks for that, Matt. I think maybe the takeaway I get from that is like, one complexity is like when I use grounding metaphor, right? There are different kinds of grounding metaphors, right? And there's like grounding metaphors to process, which I didn't really go into here, and there's grounding metaphors to like perception and space, spatial mappings. And so maybe breaking that down further, it could be useful.
Yeah, I guess maybe to actually answer your question, like in the context of designing a notational system, there are like not a huge set of kinds of spatial metaphors that we make, right? So, for example, there's like a source path target kind of metaphor where you're like walking along a certain thing. And that, for example, is a very useful kind of metaphor. And if you look at many of the diagrams that you show use like arrows in some capacity. Arrows are kind of an amazing notational tool, but they basically like embody that sort of like directional, like this metaphor of like, walking along the path. Interestingly, arrows are not used in diagrams, as far as we can tell, until like 1753 or so, if I remember correctly, which feels pretty late, right? But if you look at all sorts of writings from before then, you can like look for a long, long time. You can look at all of Da Vinci's drawings. Like you don't really see like arrows as a notational tool until they're used in this one book. And then it still takes a while for them to be used in different contexts.
What's interesting is arrows are embodied, right? Like the notion of an arrow, I can literally, like the picture of an arrow, right? It looks like an arrow that you would fire, in BC, so I think the indication, the benefit of the arrow is it makes this, it's embodied metaphor to the notion you're firing an arrow. We all understand that it's going in that direction, right, of the arrowhead. It's going in this direction. And so when it might seem like an arbitrary choice of notation, but it actually quite maps intuitively, quote unquote, to the tools that people are using in the culture, in the broader cultures. And exactly to your point, the benefit of showing the arrowhead is that it showcases where you should read it. What is the start point of the trajectory and what is the end point?
Yeah, it's like easy to learn is like maybe the most important part.
Great. Carl?
Hi. I arrived a little bit late, but I caught like a really interesting portion, so thanks. I'll look back at the recording. But I guess to reduce my takeaway here is it's really interesting how essentially notation has this sort of rich history of evolution, as you said, based on these sort of embodied experiences, human experience, and just sort of community driving these transformations in different ways. But what I'm thinking is like when you're applying this to interface or interaction design, I think that just speculating here, when you're creating a piece of software, you often want some sort of immediate result. Like this is the way you want to do it. We're gonna force a certain way of writing something or using the interface. But I haven't yet seen something that in a sort of way core to the software allows for like longitudinal evolution of how you use the software. There's nothing like that itself is designed to allow for these kinds of rich, long form personalized changes akin to like language development. So I think one direction could be, rather than asking like, what is the notation for X? It's more like, how do you support the creation and evolution of notations in a way that could lead to some coherent, interesting things, I guess, to put it very simply. That's my thought.
Yeah, thanks for that thought, Carl. That's really interesting. I have also been reflecting, on the notion of malleable interfaces or bespoke interfaces is generally framed through this immediate gratification, right? Oh, it's just bespoke right there, and it just becomes this one thing that you get. And that can be helpful, right? That can be helpful in the exact same way that, just getting code out for my informal idea is helpful. I don't want to invent a new programming language for every single thing, right? But it might be interesting, and something I haven't seen as discussed is how can we think about the malleability of software over time as this gradual process of adaptation to our usage that isn't just in the flick of a switch, we create a new UI, right? But rather, oh, I kind of like that UI. I don't like that part of that UI. I'm gradually molding it to my needs. And then it might even go into these other stages, which I discuss, where you help the shareability. So you create this malleable software, there's something you like about it, and then you're able to, what does sharing that malleable, those additions look like to other people in a community? So it's certainly sort of rich, and I'm not sure how in an HCI paper to accomplish. I think it could be helpful to people to have a whole long section about like speculative applications, perhaps.
And just to like tail end comment on that, I mean, there have been attempts, of course, like we have widgets and things that you can sort of use as plugins into systems. But I think what I'm imagining as like a different direction is not like let's make a plugin system, because that's still within a certain accepted framework of a specific application. It's more like, how do we allow people to, create their own ways of doing things? I mean, malleable software is the term you already used, but yeah, I think this would all be interesting.
Jasmine?
Go deeper on malleable software. That's sort of your software ecosystem. We could be talking about that at the level of here is your Python ecosystem. Here are the libraries you're pulling in. This is the vocabulary you have, and you must work with it through certain tools. You're more likely to be using a Jupyter notebook than an Emacs editor in this world, right? So some of those assumptions you start to get these odd, historically contingent assemblages when we're looking at how do people make horizontal moves, as Jingyi Li puts it in their paper Beyond the Creativity Support Tool, right? Manners of Power, because of platforms like GitHub playing a really central role. If you want to have something in the NPM ecosystem, it would be really convenient if you publish this to GitHub, right? So the challenge for us as if we're going to produce a general theory of how do you make notations on the computer, and why this approach of going to, oh, it's about pen interfaces is really exciting to me, is it then normalizes that huge technical mess of, yeah, this stack exists, but it's not compatible with that stack, and all these particulars. And it says, oh, but people have been negotiating these all the time. It's ultimately socially, not technically negotiated which system of notation we're going to use and which standard is going to be the real standard, not the 12th standard. So that's getting all the way to embodiment is super ambitious. Like, it reminds me of, there's some cognitive psychology work. Judith Phan's lab at Stanford is also on this metaphor visual representation beat. So that strikes me as a really formal approach to the grounding side. Conversely, on the visualization side, we have these really informal approaches like Brueggemann et al., the fold. Shared that link because the notation they're actually using to represent interactive visualization transforms reminds me so much of the notation used here in
Which one? Which notation?
there were if we could just scroll back, maybe there's a little further. Let's
The beginning?
Those. Yeah, go forward like 5 slides from here. The ad hoc extensions. 2 slides. Yes.
Oh, this?
Yes.
Oh, okay. Oh, like at the bottom.
Yeah. No, I actually mean, how do you represent the extension or the fold of a certain set of information underneath a dynamic abstraction? Like, when they say fold, they mean the complexity is still there. We can't get rid of it completely. We can't turn it into a box with certain ports on it, but we know it's there, so we can let it fade for the moment.
Yeah, one interesting thing that you see emerge is, as a notation becomes more well-known, it becomes more rigid in the sense that people are maybe more careful, at least in formal presentations, of extending it. And what they start to do is they start to not amend elements of the existing perceptual channel. They're very careful to do that, but rather add perceptual channels that weren't being used before or weren't really formally defined before. And so one example of this is really natural for us to think about is, imagine you're working on a whiteboard and you draw, a picture of a UI, right? And later on you pick up a different colored marker and you use that colored marker to describe like the layout have arrows for this layout needs to be like this. And so now you're doing a different kind of notation in line. And the semantics of the color then is a different perceptual channel that assigns different semantics to how you sort of read the notation. So the UI is in black, and then the layouts are in a different color. Maybe comments are in blue, right? And you'll see this also with more Gestalt themes. So one thing we're exploring is there are two kinds of properties. There are entity level properties, shape, size, color. And then there's also relational properties. So like, are these two entities touching or not? Are they connected or not? Is one bigger than the other? The ordering of things, right, also matter in a notational system. And so something like music notation is the combination of these different perceptual, these sort of relational and entity level properties. Music notes, for instance, the notion of size of the little dot doesn't matter, right? For instance, but maybe, if we wanted to, for some reason, if we needed to add more, like maybe the timbre or something, if we needed to say something more about the note, then maybe we extend it to a different perceptual channel. So maybe all of a sudden we have ovals, or like the length of an ellipse is now somehow a proxy for timbre or something, right? So there's ways in which this notational evolution happens through extension into unused perceptual channels.
Well, we had conductors for this, and we still do it in the classical context. But jazz, you have to be listening to the other players to figure out who's at the front, right? Who's speaking right now, and you'll call, we're going to trade fours. That has the richness of the notation at this very informal, just stand it up and we can do it on the spot, which captures some of that fluidity I feel like you were talking about with that rectangular design space.
Mm-hmm. Yeah, one thing to note here is we might not, like what you mentioned with jazz, it's not that formal. We have to be careful in saying the formal is strictly a good thing. This is actually a line between, how good the thing is, right, as well, right, how precise we are. And really, Goodman goes into this in Languages of Art. It's like, well, actually, in how music notation even is actually used, there is a level of strategic informality to it. There are things that are left out that what he argues is that it sort of, the life of playing a musical piece comes from the interpretation of the performer, quote unquote. And the interpretation is all those things that were kind of left out in the sheet music. Matt?
Yeah, I was gonna ask a question because you've looked at a bunch of these different sort of notational systems. Mm-hmm. You've been mostly focusing on like the like actual representational aspect of the notational system. So, when you're talking about like encoding across different channels, it's sort of like a visual, like information visualization view. But of course, the notation is supposed to express certain ideas, right? And when I hear the word formal, I think about like a sort of like internal consistency, the kind of consistency that like math is very good at and uniquely good at. But I'm wondering, how often do you think the like formality of the like meaning that is attempted to be represented is sort of like preceding the actual notation? So for example, in the history of math, like you have a lot of notation we use today is like remarkably new compared to the ideas that they're representing, right? So for most of history, people just talked about math in natural language. Even though the ideas were internally consistent enough to do, proper math, like the notation didn't really match that. Same with your like initial example, like the stock and flow diagrams of the predator-prey models, right? Like those are like representing something that is already well understood, but it's presenting in a different way. It seems like music notation is a little bit different, where there's like a little bit of back and forth maybe. But I'm curious, like across the different things you look at, it's like, is that like always the constants? So as researchers, so we figure out like the formal semantics for first before it even makes sense to do the notation, or obviously the notation probably helps us think about the semantics. I don't know, how does that square compared to what you've seen and studied?
Yeah, so it's a good point, right? To one thing that it reminds me of is, so Klein tries to make this argument in the book, in her book about her book paper tools about the evolution of chemical notation, specifically molecular formula, where the notation starts, of course, in this metaphor to mathematics, and there are things that are certainly break in that metaphor, right? You can't like square a material; it doesn't make any sense, right? You know, materials are indivisible in a sense, like you can't. So there's more about proportions rather than these numbers that you can keep dividing. But in the process of creating that notation, of course, like chemistry was also evolving, like chemical understanding is evolving, right? And you know, the reason you start with, I think, mathematical formula, not structural formula introduced like the positioning of the electron. It only becomes important when you start to really understand electrons at that level, what electrons are shared, what electrons are not. And there are cases in which Berzelius is actually, she shows that Berzelius is extending the notation in ad hoc ways, and I'm going to include this in the paper that I write up, where he's like really uncertain. And the process of extending the notation is almost the process of like declaring your beliefs somehow, right? Sometimes, especially in scientific development, it's like you're declaring a belief, and you're like, if this is true, then you know this notation, this little extension helps us think through that. And then I think through the process of trying to use those extensions, we learn if they work or don't. You know, there's an element of the community uptake, right? I wouldn't say that's purely a usability thing, but usability certainly plays a role. And then Klein makes the argument that the notation starts to lead. So people start to publish papers that the whole thing, there's no experiment at all. Actually, people in chemistry get very annoyed, where all it is like a derivation in molecular formula. And then the derivation comes to, oh, well, we should see this, or we should see this kind of these kind of compositions in the experiment based on these derivations, right? Which is really interesting. So it starts to lead theory. And so that is productive, she argues. But I would also say, like, every notation encodes a perspective on the situation. It is a model of the world. And especially for complex phenomena like chemical compounds changing in reactions, there's a lot going on there, and there's a lot left out of the model. And one of the interesting things I wasn't able to include here is there is an old notion of formality that comes up again and again, actually, that is kind of hidden, which is there's a definition of formality that the formal is something that's almost without meaning. We just do it without thought, right? This stems from the very early institution. It's like a ceremony. We just do it as a ritual. We do it because it's a formality, we say. It's a formality, right? And that notion of formal, I think, reflects back at us because we see in music notation, in the sort of critical histories of how these notations are used, if they become popular enough, they start to become the chief lenses through which people view the world, and the chief lenses through which people value certain things about the world. The argument in music notation is sheet music notation doesn't really care about rhythm, right? It cares a lot about melody. It foregrounds melody. And so the argument is, looking into the history of, particularly the Western history of, what was uplifted in musical schools, they uplift this analysis of memory, and everything outside of that is sort of not really music theory. We don't really care about it as much. Yeah, it exists, timbre, it exists, but it's not really relevant, or it's not super important. And I think we see this also with computing. We see these kind of like aesthetic biases which emerge among people who are, strong members of the community who love to use the notation over time. You will see, I guess an instance of this is, you will see in like machine learning papers contemporary machine learning papers, practically speaking, it's most likely code, like PyTorch or something, that they're creating their new innovations with, but they're going to have to express that in the language of formal mathematics when they present it, right? And that's not necessarily even the language they use to think through the problem, not always. So it's almost like that's a formality, right? So there's a kind of murky aesthetic notion of formal that is important for us to keep around.
Yeah, the question about like the notation like says something about what you think is important reminds me of a story from like conversation analysis. So like people started doing conversation analysis in like the 50s or so, and they do a lot of the work like over the phone. And so for the way they do conversation analysis is by making transcripts, right? Just writing this person said this, this person says this. And that seems uncontroversial, but of course, if you're interested in like how people are communicating, that like gets rid of a lot of information, right? And so eventually you see notational systems developed for capturing the fact that like, you know, someone is like interjecting or is like saying something at the same time, or like even when they're coughing in a conversation. And it turns out that there's a lot of stuff there that you could care about. And there's like the notation reflects like what people realize is actually important to focus on, which I've found interesting.
That's a great.
Thank you.
Yeah, thank you everyone, and thank you Ian for the great talk. I think we're on time, so we'll stop there. But please, you know, if you have any further comments or questions, please let's use the Discord chat. I actually had a bunch of questions, but I will take it out with Ian separately. But yeah, thank you. Let's thank Ian again for a great talk. I really enjoyed learning about this topic, and thank you for sharing it for us. It's a really important topic. So. So I will send out the recording later through a letter, but I think, and for the next month, I think we'll skip, but yeah, we'll come back probably in September. But thank you everyone, and have a great rest of the day.
Thanks everyone.
Thanks, y'all.